Okay, so hi everyone. Welcome to this research seminar. I will turn on the camera so that you can see me as well. I'm here with Abul Hasan, and Abul was a TA in our department. How many years ago was that?
5 years ago.
5 years ago,
Yeah.
and he's now a postdoc.
Yeah.
In which department?
In Institute of Health Informatics. It's under Population Health Science.
Okay. And he's working on natural language processing and deep learning. Uh, Thank you for coming to give this talk. And the title of the talk is Incorporating Dictionaries into a Neural Network Architecture to Extract COVID-19 Medical Concepts from Social Media. So I will now turn off my camera, and Abul, whenever you're ready, you can start.
Okay, thank you, Antinos. So I'll start. And first of all, thanks for giving me this opportunity to present my research work, which I did during my PhD. This was the last piece of work that I did during my PhD. And so about incorporating dictionaries into neural network architecture. So I can't go next. Can I go next?
Okay.
Okay.
Yeah.
Do you have to request you to go to next again? Let me check. Oh yeah, I can go now.
Okay.
Yeah. Okay. So the plan of the talk is I'll provide a brief introduction on what was the aim of this research and goal and aim, and I'll do a background on deep learning and NLP, which, as I can see from the audience, most of you know. I actually prepared this presentation thinking that the students will be there, so probably it won't be that helpful for you. So most of the stuffs you know. So
we will share it with the students.
okay.
So yeah.
Yeah. And then I will talk about health information extraction from social media. That was the main topic, and utilities of dictionary. Then I will conclude the presentation. So, uh, so my main aim was during my PhD, of course, was to extract actionable health information from social media posts that is there on the screen at the top portion of the screen. So I'll just read the thing just to start with. So hi, the neurologist started me with pramipexole. Can you see there is a difference? I mean, probably that is not the right spelling of the drug, and the bracket is D is the drug. I did not. NZ means it's a negative. By the way, these are all annotations. I did not like it. P means positive, means it's a positive thing. It is not positive, so because there is a not. So it made me sleepy, which is a side effect, and did not seem to help with my movement. That is the target symptom that this medicine was actually taken. Now, during my PhD, I did a few work on how to make sense of these type of posts and using rule-based system and machine learning algorithms. So, for example, in this case, uh, pixel is not helpful for the movement. So I created relation extraction system. So and then from there. But one of the thing is important when I created this type of system, which makes sense from the text, is that recognizing medical entities or concepts, I'll say, uh, from the text. So concepts means, for example, parmimexel over here, drug, and then sleepy is a side effect, and movement is a symptom. So later on, my focus actually shifted to how effectively we can extract these concepts from the social media. Now, now currently, I actually this just to connect the current situation. So probably large language models uh, process the capacity to extract such information without any training data. So, but the computational resources required often exceed the reach of many organizations. For example, NHS, as you all know, they still have had to send letter without using email. So such large scale systems are not applicable to the mm, uh, big corporations like NHS, which is very important. So so herein we propose is still we think I think that this is relevant, this kind of research. So we propose a deep learning model that would require less computing resource but are highly precise. So that was the goal. And now I know you all know all these things, but I'll carry on saying a bit on this. So, so the background on this is that before the era of generative AI, it was bidirectional encoder representations transformer BART, which is actually kick-started the LLM drive. And BART is based on transformer architecture and pre-trained using uh, Google Book Corpus and Common Crawl. Excuse me. So Common Crawl is a all the web text being scrolled and put together in one place and stored in there. Now, this transformer architecture is pre-trained on masked language modeling, which is called MLM objectives. That means that just predicting some tokens which are being masked or blank. So that is the main difference between the GPT-based generative AI and the MLM is that GPT actually predict all the tokens in the sequence and it goes long, it goes till very long for the long sequences also. For example, GPT 3.5, they actually predicted sequences which has 32,000 tokens long. So they're powerful. That's why this simple technique actually has shown be very powerful in modern AI NLP tools. Now, so so that is actually the current state of the technologies, and then I will start a bit further back. So starting with the natural language processing. So to process a text, we employ what we call NLP pipeline, which pre-process the text into machine readable format. So the basic unit of a piece of text is a word, and we need a vocabulary of words for text processing using a neural network. So we have a what we do, we process the text, and then we identify all the unique words in the text in a corpus. So that essentially creates the vocabulary. Now, one of the earliest NLP tools developed by Google research team was Word2Vec. What they do, so by utilizing this vocabulary of words, Word2Vec creates word vectors that encode semantics of a word in different directions. So a word, for example, in my case, tired, could just say could might actually signals that I'm just tired, no underlying conditions. But if it is in the context of, for example, in the Parkinson's, tired is a kind of symptom of Parkinson. So essentially, word vectors can actually capture meaning from different directions. However, the word vocabulary is fixed, so we cannot create essentially word vectors for all the words in the world. So what Bart came up with the idea is called word piece tokenizer, which essentially breaks down a word into several segments. For example, in here I've given an example, meron penem is a drug, is segmented into 4 pieces, me, rop, nm. So as you can see, this essentially does not actually convey any morphological meaning in the sense of English. It, these are just pieces that are very prevalent into the corpus that has been word piece tokenizer has been trained on. So there is also a research drag in myself. Actually, I'm doing this kind of work now at IHI. So how to create effective tokenizer. So so BART actually instead of having a whole word sequences, they have these kind of word piece in their vocabulary, and the original BART has 30,000 word pieces in there. Now talk about the difference between word to wake and BART's embedding, word embeddings. So as I said, in case of word to wake, we have whole word as a whole word in the vocabulary, and vocabulary could be 50,000, 100,000, whatever it is. And each word, if the vocabulary is 50,000, the vector size is 50,000, and only there is only one in one of these 50,000 places, elements, only in one place it is one, where it actually maps with the ID of the word. So essentially, this is a 50,000 vector and sparse vector, which has all zeros and only in one place in one. So we got all these, let's say there are millions of words, and we have got 50,000 unique words in this million words corpus. And then we got this 50,000 one hot vector, what we call one hot vector. And this goes into the into embedding matrix, from there into a linear network, linear neural network, and projects to the matrix in a hidden matrix, and then tries to predict the context word given a window of 3 words. In word to wake, they actually have 3 to 5 words prediction window. And this matrix in the green actually is the hidden matrix, hidden weights of the network, and this is called context matrix. And during the process, during the prediction process, so the weights of the embedding matrix is changed from 1 to in real numbers, and depending on the context, and that becomes the word vectors. Actually, that is the word vector is a vector of, let's say, 50,000 in this case, in this particular case, and we'll have 50,000 real numbers in there. So which means something in different directions. So that's the static word embeddings. Now from the static word embeddings in 2015, we come to the contextual word embeddings. So BERT creates actually word embeddings called contextual embeddings that changes as the context of a word changes. So every time we put some word into this BERT, we'll get different kinds of embeddings depending on the word context. But in the case of word to wake, we wouldn't get different word embeddings, but only one single embedding for each word. So that is the difference between word to wake and BERT. And actually that started shifting the NLP research to the direction that we have in generative AI now, right? So these word embeddings are no more fixed word vectors, as I said, rather than the simply weights of the embedding layer of P10 transformer network. And so because word to wake and BERT, both models are actually trained on the similar corpus, so people found that there is connection between uh, contextual embeddings and static embeddings. So in my research at the time, so I'm talking about in 2021, 2020. So at the time, so it's like we thought that, okay, why not concatenate both kinds of word embeddings and put it into a different architecture, which I use LSTM CRF architecture in my case, in order to extract concepts from the text. So that's what I did basically. And then we use supervised machine learning, meaning that we have annotated corpora. And also the formal name for this kind of research, I can say I did, is called named entity recognition, or NER. Now, now I'm coming to the why we need these kind of system in health or medical or biomedical. So now I'll say from the point of view of social media, though I'm working on the real electronic health records now, but social media is also not less important, I found. So now these, for example, during the pandemic time, it was very helpful, to track people what are the prevalent symptom of COVID-19, right? So imagine there is a future pandemic, and if you have a system ready, we can actually extract information from the social media, live social media data, and we can generate effective pre-warning system for the for the population health for the population health. Now, one of the challenges of this kind of system faces is that social media people use diverse phrase and phrases and words for expressing similar diseases. Oh my God. So, for example, fever, which is a colloquial term, or for more formal medical term is pyrexia. Doctors knows pyrexia, which is fever, and but people use high temperature, feverish, and temperature. So as you can see that there are lots of variation in these terms. And also, for example, another example is shortness of breath. These are all very, these are actual symptoms of the COVID-19. So shortness of breath, which is in the medical term is, clinical term is dyspnea. And people use short of breath, breathlessness, and whatnot, right, to express the same thing. So uh, we have UMLS ontology already for extracting these kind of uh, symptoms from the text, but UMLS is not fit for the purpose is because uh, people invent new terms, and also those, where when those terms are incorporated into UMLS, it takes 2 to 3 years. So, for example, shortness of breath or breathlessness probably not was in the UMLS ontology, but if we had used UMLS ontology to catch that, uh, it would have missed, right? So how do we go about with that, right? How do we? So one of the very simple solution is to use dictionary, right? So when it's very easy to collect dictionary. For example, I collected during the pandemic, I collected about 4,000 terms and created a dictionary, which we call in this dictionary symptom COVID-19 symptom dictionary, which we have used in our model. Now, dictionaries are lightweight and they can be expanded and maintained very easily. And they can also be used as features to the machine learning algorithm. And then the third and the last, and they're very important, they are useful for as a weak learner. And I will say about this in my conclusion why weak learning is also important in the era of generative AI. Now, what we did, I have only for only 7 minutes, so I'll try to finish. So what we did, given a piece of text, right, as you can see in different colors in the text. So headache, say weak. Headaches means that's a symptom. We have, I've seen shown here 8 dictionaries altogether. So given a sentence or a passage or a text, so we identify which word comes from which dictionary, and we have created a vector of 8 dictionaries in this case, D1 to D7, 7 dictionaries in this case. So, and we created a one head hot vector for each token. And of course, it's not a one head hot vector, it's because one token can actually be in 2, 3 dictionaries. So it will place one in those places. So anyway.
So these are overlapping dictionaries, and
Yes, overlapping dictionaries. Yeah. So we created a matrix for that. And then, as I said, we used LSTM CRF. So we create two architecture. Given an input sequence, it goes to the embedding layer. I'm talking about figure A, goes to the embedding layer. Then from the BiLSTM layer, goes to the softmax and CRF, and then it decodes the concept. Now, dictionary vector that I've shown in there has been actually appended at the second layer. So we found that if we add dictionary vector with the input sequence, it is not effective. Actually, if we incorporate dictionary vector can be seen as a knowledge. So if we incorporate knowledge at the layer that is very close to the classification layer, works well. So that was my finding during this research. So we appended this dictionary vector in the second layer of the BiLSTM network. And this is the figure A. And in figure B, in the figure A, we use embedding layer static embeddings. And in figure B, we use static embedding plus the BART. And then we concatenate. But there is a challenge in there because embeddings are for whole word. On the other hand, BART's embedding are subwords. So the way we actually did it, so if a word gets pieces into three places, and we got only one embedding from the static embedding, so we copy the word embeddings for three pieces, for the three pieces. So that's how we solve this problem, and then we can concatenate that to the BiLSTM layer, and then we decode the concept. So this is the architecture and how it works. And then what is the main contribution of this work? So I would say the main contribution is that we have shown that we can achieve performance very on par with the BART tweet, which is the kind of BART that we used for our social media dataset because it is from Twitter. So we use BART tweet. And then we show that, as you can see for the last row of this table, LSTM network that we have used is actually works pretty well using the dictionary 81%, and BART tweet goes till 80%. And this is also about without using any annotated data. So for example, we have this dictionary, symptom dictionary we created, and then we annotated the data automatically with the dictionary, which we call weak learning or weak supervision. And then you can see from 0%, if we did not have any dictionary, did not have any dictionary. I mean, we have obviously a basic dictionary, and then we started incorporating more and more words. So, and then when you don't incorporate anything, the result is only 70 to 70%. But when you start incorporating more and more terms, which is related to the COVID-19, it goes to the 81 and 80%. So the finding is that, first of all, dictionaries work, even though BART tweet has been retained on very large corpora. And using the dictionary, we can achieve better performance using LSTM. That was the main contribution. And then the conclusion, I've got 2 minutes. Now,
you have more if you want.
Okay, no. And so dictionaries are interpretable, and models built using dictionaries are easily explainable. Why? Because if a model makes a prediction and we know that there is a term in the dictionary, so it is explainable in a very simple sense. But if then we can quickly create demonstration samples using dictionaries, which could be useful for few short in-context learning, and which actually it remains to seen how this weak supervision will work in context learning systems, for example, GPT-3, if we use the same weak learning, how it will work? That is actually a research question that I'm thinking of. And another thing is that dictionaries can be used as a retrieval augmented excuse me, text generation using generative AI. What I mean by retrieval augmented text generation? For example, we can use dictionaries to fact check that the text generated by the GPT-3 models. So if we have a very good dictionary like COVID-19 symptoms that I have built, and we can actually do the fact checking using the dictionary when they generate the text. Yeah, thank you.
Okay, thank you very much. I will stop the recording now so that we can start the discussion.
Yeah.
Okay.